Sabe por quê? Uma coisa, sabe o que a gente achava a pessoa falando? Eles concordaram com o que ela falou. O equipamento é de menos. Tem que achar uma coisa pra cá.
Dos anos 50 são aquela escola, isso é bom, cara.
Isso aí é bonito.
Eles não são muito você está pensando se ele ver um barzinho, tomar um café. Isso. Vai inundar de chegar lá no final. Lá é bom, né? Você olhou o carinho de lá? Isso. Só por isso que se for pela terra, hoje não é mais relógio. Mas que camisa, a galera gosta. Mas que camisa. Ah lá, que legal. Mandou o vídeo lá. É, cara.
Deixa eu fazer uma pergunta, precisa vir com a fone?
Na verdade, eu tô pegando esse negócio consegue. Ele topou um tem uma plenária foi difícil. Olha só. Ele ficou lá em cima?
Lá em cima.
Tá.
É que ele tem duas angulações, 90 graus ou 120.
Tá.
Então eu coloquei 90 para ele fechar mais e eu consegui pegar. Né? Mas aí se precisar deixar do som lá na frente que eu vejo que tá baixo, eu levo esse aqui.
Tá bom, tudo bem.
Entendeu?
Tá bom.
Mas a gente dá um jeito.
Tá bom.
Pode isso aí.
Today, it's a pleasure for me to introduce to this audience Professor Robert Stamps. Robert Stamps is a professor at the University of Glasgow. His work is in the area of unicellular physics on the topics that include brilliant light scattering theory, nonlinear excitations in magnets, spin and charge transport in magnetic metals, and electromagnetic excitations in unstructured magnets. His main interests at present are unusual creep phenomena discovered recently in low-dimensional magnetic systems, and ordering process in a new class of frustrated and disordered systems called artificial spin ice. So, I hope that you will enjoy and learn, like me, in the opportunities that I had to hear Professor Robert Stamps. So, and I would like to thank you very much, Professor, for the invitation to be here to give this talk in this school.
Thank you very much for the opportunity to visit. As I mentioned, I think I visited here once before for just a day, but that was 8 years ago, so it's a pleasure to come back to see again this beautiful place. Also, it's a nice opportunity because this is a winter school, and I think I just 2 weeks ago was in the Northern Hemisphere at a summer school, so it's unusual to be able to give within 2 weeks both a summer and a winter school lecture. So thank you.
The same weather.
No, it was much hotter there. But no, very good. Yeah, good. Before I start, let me just try to understand, how many of you are working in magnetism? And how many of you are working in optics? And how many of you do something else entirely? Okay, so I try to make it general, but please stop me with any questions that you have. So I'll start. Somehow got 2 buttons here. So what I'll talk about, I was asked to talk a little bit about magnonics, what that is. So what I will describe is high frequency magnetic excitations And some of the things which we've been working on in the last few years, which are which lead to new materials and new ways of controlling and even generating magnetic excitation. And the part of the motivation is application. And so this is just an example of applications. We call it magnonics, patterned magnonics, just meaning that you can control better the magnetic excitations by doing either micrometer or even nanometer scale lithography. And so these are some metamaterials, I think, that maybe will be discussed tomorrow. And these are some other types of circuits for manipulating microwave frequency waves using magnetic materials. These are examples of other more advanced techniques where one tries to control the wavelength, frequencies, and even the phase of magnetic excitations. So one application for these is spin wave logic and alternative platforms for doing computation, classical computation. So this is an interferometer where you can adjust the phase of one arm, interfere the waves being detected. This is a schematic for a logic device with inputs and outputs. And these are some of the components that go into these, which are materials where you can control the magnetic ordering and change then the behavior at gigahertz frequencies, and different geometries and different structures which are explored to try and do that. So I also will present works from quite a number of different collaborators, literally around the world. How many of you here are PhD or master's students, graduate students? Well, the results I'll show you are from people who are doing this work as either part of their master's or their PhD degrees. That's in dark, bold font here. That's from Germany and Japan, and own students who are at Glasgow, but there's from Mexico, from China, and from the northeast part of Brazil. So really a bit of all over. And I'll show you some of their results. I will show you examples of. So the outline of what I will talk about in the next hour is we're looking quite a lot at chirality in magnetic systems and how that chirality can affect spin wave excitations, magnetic excitations. So we look not only at the structure, but in particular at how magnetic information propagates through a system which has a magnetic chirality. And I'll talk about this in two different ways, just propagation in materials, but also how one can create confined regions which you could measure using some sort of ferromagnetic resonance, for example, directly effects of this chirality interaction. And then I'll talk about a conceptual idea, a scheme of using patterned arrays, which many people have studied as artificial spin ice, but instead using them as microwave devices or materials that can be configured and reconfigured. So you could change the magnetic properties, certain magnetic properties, just by changing the ordering of the magnetic moments inside these arrays. And then lastly, if there's some time, I'll talk about some work. It's a collaborative project also with a group in Brazil, Tom Domolo. And this is work on anti-ferromagnetic optics, if you will. And there's analogies. It's a single material which can behave as a negative index material and as a slab lens. It has a hyperbolic dispersion. So I'll try to just show you a little bit of that, which is very interesting, what one can do with anti-ferromagnets. So first of all, because I understood that there be many people who are not familiar with spin waves, even if you're working in magnetism, that's sometimes not something we come across all the time. So let me just start from the beginning. What do we mean by magnetic material? I mean some sort of a material where there is magnetic moments which ultimately are created by electron spins in orbitals, either extended or quite localized. And then there are interactions between these magnetic moments which can lead to long-range order and a magnetic phase. So these are just examples of ferromagnetic phase where everything is lined up, or one can have much more complex phases, the simplest being antiferromagnet, where there's no net magnetic moment, but magnetization, but their local magnetic moments are just antiferromagnet, so they compensate. And then there are variants of this where the magnitudes may not be equal depending on their direction, orientation. And then other systems, chiral systems, where there may be a twist in the magnetic moments as you move through the material. So there's quite a rich phase diagrams depending on what system and material you're looking at. And one can study these from point of view of statistical mechanics and critical phenomena. Many of them very beautiful model systems. But I'm going to talk about studying them from dynamics point of view and the high frequency excitations. So, if you imagine you're in some sort of an ordered state, let's take a simple with a ferromagnet, and if it's perfectly ordered, then all the moments would line up parallel to one another. But that only occurs at very, very low temperatures. And at any finite temperature, or even at zero temperature with quantum fluctuations, there's some probability that one of the spins or moments will be flipped. So it's not perfectly aligned. And you could think of an excitation where there's one flip, but you don't know exactly where it is, and that would be an excitation. You might call that a spin wave. And if we think of it classically, which is how I will for this talk, instead, it's important to remember these are magnetic moments. Magnetic moments have angular momentum. And so the dynamics of the magnetic moments is precession. So they are not arrows that rotate like this to align next to a field and minimize their energy. They always precess. That's a nice classical picture that captures the intrinsic angular momentum which magnetization represents. So there's always a precession, so the dynamics, the spin wave dynamics, be thought of always in terms of some precessional cone. Now, the picture then would have is this. If this is our ground state, ferromagnet, all the arrows aligned, then an excitation above that ground state, which is distributed across that line, would appear like a coupled precession. So if you looked at the cone of precession, there would be a long wavelength excitation where these are all together precessing exactly in phase, or a shorter wavelength excitation where then the neighboring phase changes, and then this involves a great deal of energy because the system is trying to order along particular directions. So this would be a low energy excitation, and these would be high energy excitations at finite wavelength. So tomorrow in the lectures I'll go into more of the theory, and you can understand how these are actually bosons, and you can use all the things you know about bosons for calculating thermal processes. But what I'll talk about now is how the spin waves travel, how they can propagate. And so this DMI is a shorthand for Drylazinski-Maria interaction, which is the name we give for a description of chiral interactions that lead to chirality in magnetic systems. So let me explain this. If a crystal has inversion symmetry, So if it did not look like that, but instead if this dot were over in the center, and I could invert all the atoms and still have the same crystal, then the energies, all of the energies that describe the physics of the system would be consistent with those symmetries. And one of those, the ordering energy, which ultimately has to do with electron overlap between moments situated here and moments situated there, that energy also has to obey the symmetries of the crystal structure, the material structure. Now, in that case, I do not have chiral interactions. Ferromagnetism can have antiferromagnetism, can even have a helical type order, but there's no preferred right or left-handed chirality. However, if we move one of the atoms away so that we no longer have inversion symmetry, then new terms are possible. They may not exist, but they are possible. And these terms will have a form that we can determine by the symmetry of the system. And the important thing is they involve an energy which depends only linearly on the rate of change of the magnetization. So if I had perfect symmetry, it wouldn't matter. It would never get these linear terms. It would always be quadratic, which means that what that would translate into is a spin wave traveling to the right at one frequency would have exactly the same wavelength as a spin wave traveling to the left. But when we break the symmetry, and we have these gradient terms, these linear gradient terms, then spin wave momentum going in one direction can have an energy which is different than the same momentum going in the opposite direction. So you've broken a symmetry between energy and momentum. So if you reverse the momentum, you would have to have a different energy if you lower the symmetry of the crystal in this way. And one way to do that is with a bulk, a large volume crystal. And indeed, one discovers then that these interactions can appear, they can be quite strong. They can give rise to non-collinear ordering. This can appear as helical structures, or something which is very popular and interesting at the moment is that it was discovered just a few years ago, they can lead to skyrmion structures, which are localized magnetic twists that can propagate without changing their shape, to carry information. So these are all very interesting things that can happen when you introduce these new type of interactions. But another way of doing it, to break inversion symmetry, is actually very simple. And for many years, many of those of us working with thin film magnetism have been dealing with it, we just didn't know. And that is simply if you have a film of one material and then another film of another material, so say this is magnetic and this is one interface, it's not even magnetic, maybe this is platinum. And up here you've got vacuum or some other material, so that the interfaces on this magnetic element are different. This also lacks the inversion symmetry. And this also then can give rise to an interaction which can lead to chiral ordering. And this is particularly exciting because it's been now shown just this year that one can create these skyrmion-like structures at room temperature in just thin films of cobalt on platinum, for example. And one can start to produce these objects and study their behavior and manipulate them. So this is all very exciting and all very new. And the mechanism, however, was for this chiral interaction was predicted many years ago, both by Fert and also discussed by others. And the essential idea is that if you have a metallic ferromagnet and it has spins, the spins can interact via conduction electrons near the interface, and these conduction electrons, if they are traveling through a region with a large spin orbit coupling, then that can rotate the spin's information between one and the other lead to a non-collinear interaction, a chiral interaction. And so that was predicted, and now it's been confirmed, and we can see the effects. So one of the effects then that I want to talk about is what happens to the spin waves which travel on such a material. So remember, the magnetic moments are angular momenta, and so they always precess. And so a spin wave traveling in a ferromagnet would look like a series of precessions as you go through the wavelength of the wave. And the fluctuations are always transverse to the magnetic moment. So it's these precessional amplitudes are the fluctuations. So if we look at the top here, just on the top view, and trace just the arrow here, then you see very clearly that's a spin wave that defines a wavelength, and it's related to the rotation, the precession of the moment around this cone. And this, if there were no chiral interactions, this wave would have a frequency that is independent of the sign of its momentum. So it would just be some function of the momentum, but it would be perfectly symmetrical. Here's the frequency, here's the wave vector of plus and minus. It'd be perfectly symmetrical. And at the longest wavelengths, it is something that looks like a K squared. So it has the same dispersion as a free particle, a non-relativistic free particle. And it's perfectly symmetrical about zero wave vector. If you include a Dzyaloshinski-Marie interaction, this introduces, because of these linear gradients, a term which is linear in the propagation momentum. And so the energy depends on the sign of the propagation. And what that means is that instead of being a dispersion relation which is centered about zero momentum, it's off-center. The minimum occurs at some finite momentum. And whether it's positive or whether it's negative is determined by the sign of this chirality. So that's a very striking effect. What it means is if you study a spin wave traveling at a constant frequency, if there was no chirality, it would have the same momentum, regardless of whether it's going right or left. But if there's chirality in the system, it doesn't even mean chiral ordering. It just means a chiral energy. So it can be still ferromagnetically ordered, but with this chiral interaction, the dispersion is shifted. So, and it's shifted with this linear contribution. I'll talk about this shift in many different ways, but that is the main striking effect on the excitation spectrum of these modes. So one can simulate and calculate this using various numerical tools. This just illustrates one result. For those of you who work with magnetism, how many of you use micromagnetics? A little bit. So you do these micromagnetic simulations with WUMF or MUMAX or something. MUMAX. Okay. Yeah. This is a simulation from MUMAX, in fact. And what it is it's just a numerical tool for integrating the classical equations of motion that describe the precession of the spins in the system. So you imagine a film, and you discretize it, and you calculate all these coupled torque equations that describe the precession, and this is a numerical way of doing it. And so this is an example of a source, an antenna, which is creating spin waves which travel to the left and to the right, but it's a nanostructure, it's a wire, and if you look carefully at the waves which are propagating away from this antenna, they have different amplitudes depending on which side of the stripe that they are propagating on. And so here it's very clear. Here's the antenna, here's the amplitude of waves which are localized to the edge, and they're localized to this edge traveling in that direction and this edge traveling in that direction. So that's an example of how a nanostructure can modify, and together with chirality, can modify propagation of the waves. And we've looked at that in more general terms for propagation on stripes, or propagation along dots, or propagation through domain walls, which I'll talk about in a minute. And so in all cases, because of the chiral interaction, the edges are special. They may even be tilted a little bit, and the waves will propagate at one frequency only in one direction with respect to the edges. And to go in the opposite direction, they have to travel in a different frequency. So for people who are interested in applications of magnetics with pattern structures, this is all very interesting, because you can now break the symmetry of going to the right or the left, or going clockwise or counterclockwise, and start to think of devices that can use that. Now, the other thing, which is in this picture, is what happens if the order is disrupted by a transition, or a boundary wall. And we spent quite a lot of time at that, because it has some interesting features. I'll show those to you now. These are domain walls, and I've shown you an example of a wall, a domain wall, but it's not magnetic in this case. This is a structural domain wall, meaning that it's a transition region from one phase to another phase. Here, changed only by the slight ordering. And so these are regions of uniform order, and a transition region where that order changes in some way. And that's what a magnetic domain wall is. A magnetic domain wall is how the magnetization changes from one orientation to another orientation. So even a small element, if you were to reverse the magnetization, how does it happen? Well, it's most likely to happen, if the element is large enough, by nucleation of a small reversed region, such as this region inside that, usually it's in an edge, and then there's a transition region, which is a domain wall region, which then propagates and moves through the material and letting this domain grow at the expense of this domain shrinking until it's reversed. So the domain walls have a dynamic all of their own, and they mediate these type of processes. And when I talked about skyrmions, mentioned skyrmions, a domain wall is essentially a one-dimensional analog of skyrmion. It's an object which can move. It's a solid object. So the domain, what we were interested in, so here's a picture of it. There's a region where in a ferromagnet which points up, a region which points down, and the transition region then is a well-defined, localized wall which has a definite energy and can move freely if there is no inhomogeneities or defects in the material. So it costs no energy to move it in a perfect material. Now, what's interesting about this is, in a perfect material, if the wall can move, how do spin waves interact with such a wall? So, if we think about that, it's a scattering problem. So here's a domain wall, ferromagnet pointing up, ferromagnet pointing down, a transition region in between, and a spin wave incident on it. Now the interesting feature here is that it turns out that the perfect ferromagnet, without chiral interactions, the domain wall doesn't do anything to the spin wave. Well, that's not true. It does one thing. It shifts the phase. There's no reflection. It's a reflectionless potential. It just has exactly that profile that it belongs in the class of reflectionless potentials. You come across that sometimes in optics or quantum mechanics. The spin wave will travel across the domain wall, and its phase will be shifted, but there's no reflection and no transmission. So that's why we were interested in how do spin waves travel when they scatter through a domain wall. If it is perfect domain wall, but now there's a new interaction, a chirality. Well, if you add chirality, it changes the shape of the potential. It looks very similar, but it does change it. And it's no longer just a shift. It's now a reflection and a transmission. And so what happens is that the domain wall has excitations which are localized to the domain wall, but now they mix with the spin waves that can travel across it. And so now you can have energy being transferred from a spin wave to the excitation in the domain wall, which then couples to spin waves on the other side. It can transmit the spin waves, and some of it, though, is going to be reflected. So that was our first thing we learned about this. And we can calculate then, in analogy to one-dimensional quantum mechanics problem, we can calculate a transmission and a reflection. And most importantly, we see then that with this chiral interaction, there's a gap which opens up between the modes which travel across to the right and to the left. They fall on different branches. This is the non-reciprocity appearing. But there's a gap which appears, which is directly proportional to the chiral energy inside the domain wall. And this is what's mixing the waves and allowing this to happen. For magnonics, we thought that was sort of an interesting idea, because we could imagine a stripe of domains pointing up, pointing down, up and down in a stripe, and in each region there's a domain wall. And the domain wall acts like a barrier potential for the spin waves. And so one can have partial reflection and transmission of each one of these barriers and create, therefore, an artificial band structure. So this would be Bragg-scattered spin waves, and every time there's Bragg scattering, where the wavelength of the wave just matches the periodicity of the domains, we would get a gap opening up, where the gap is due to the Jaroszynski-Maria interaction. So this would be an example of a magnonic crystal. It's a crystal where you've engineered the band structure for spin waves traveling on this and introduced, well, in semiconductors we call it a superlattice. But it's analogous to how electrons would travel through a periodic crystal. Instead, these would be magnetic waves, the frequency and the wave number, and these bands which represent diffraction from the structure of domain walls. Yeah.
These are simulated results, or?
Yes, these are simulated. Someone would like to build it, that would be interesting. Now, there's another thing which appears. If you remember, I said that in the domain wall there's a localized mode. Well, that also is an interesting object, because what that means is if you have a domain wall and you excite a spin wave to travel on that domain wall, it will follow that domain wall. And so imagine a domain wall, and now rather than scattering, we're going to travel along it. In such a case, that means you can actually curve the domain wall and redirect the spin waves traveling on the wall. This does not require chiral interactions. The chirality here simply stabilizes the wall such that you can bend it like this. But what is special about chirality is that you can imagine a striped wire. This is a bent magnetic wire with magnetization pointing up, down, and then up again. So there are two domain walls. This is like two railroad tracks. And spin waves traveling along the railroad tracks don't communicate because they're localized to the wall. And one can be going forward and one can be going backwards even. And so they're traveling even at the same frequency but with different wavelengths. And one can bend these walls around inside the material. So here's a picture of it pointing down, up, down. And these are the two domain walls, and those are the two tracks, two train tracks, which the spin waves are traveling on. And we can start to think about building devices, in fact, where you curve domain walls wherever you want, and therefore guide the spin waves. So, if you're working in photonics, you do this all the time with fiber optics. This is the magnetic analog to a fiber optic cable. And you can bend it and manipulate which way the spin waves travel. Now, these are simulations, but I can say that people are starting to try to make these. Okay, now that's one type of confinement. Let me talk about another kind now. If we think about non-reciprocity, and what happens if you're trapped inside a region? Just before I start that, I should ask, how much time do I have? It's okay? 30 minutes? Oh, okay, good. Okay, so, here's the picture. Now, don't think about spin waves and magnetism. Think about this. If we have a free particle, it's got a nice energy, goes like the square of the momentum relationship, which normally you would say for zero momentum, the minimum energy would be here, and it would be zero momentum. But suppose, somehow, the minimum is shifted away from zero, so that two excitations, two waves, traveling at the same frequency, but one going to the left and one going to the right, have different wavelengths. Now what happens if we have mirrors that reflect those waves, and we trap them between the mirrors? Well, if we're traveling to the right, we have, according to this diagram, a long wavelength. If we're traveling to the left, we have a shorter wavelength. What happens? If these wavelengths were the same, we know exactly what would happen. We'd have interference with well-defined position of nodes. So there would be, depending on the wavelength, we'd have a node in the middle maybe, and maybe a shorter wavelength. We'd have two nodes off to here, but they'd be well-defined nodes. Introductory physics. What happens now when the wavelengths are not the same? The energy is the same, but the wavelengths are different. So we wanted to look at this problem from point of view of magnetic spin waves, because these systems really exist. You have a material, it's not moving in your reference frame, but it appears to be something like a Doppler shift on the spin waves, and they're bouncing back and forth. So we did calculations, but we also did some very nice simulations. This was Benjamin's work, and he used Mumax again to do these simulations. So it's a magnetic element, an ellipse, and you excite the normal modes of this ellipse. So these are maps of the precession amplitudes at different frequencies. These are the normal natural resonances of this dot. These are magnetic resonances, and this is the distribution of the amplitude, the intensity of the excitation. And the largest excitation is one which has its largest amplitude near the ends, and a minimum amplitude in the center. And then the next highest excitation has two nodal lines, and a large amplitude in the center, and also at the edges. So these are the standing waves we would expect, the two lowest energy standing waves we expect for this geometry. We chose ellipse because it simplifies the distribution of magnetic fields produced by the elements. So, but that doesn't change the physics. You still have reflection of the waves. The two nodes. Now what happens when we put this chiral interaction in, so that the wavelengths are different at each frequency? Well, the low frequency mode, the lowest one, is still has a minimum in the middle, but now it's a well-defined node, and the two amplitudes at the end. We still have this excitation as well. We see then nodal lines here, nodal lines here, and we again have almost the same structure. This peak has appeared. It was here too, but it was very, very small. But this peak now is much more pronounced, and it's one with an additional nodal line. So you see a sequence of standing modes, exactly what you expect. So you might say, well, it would seem that chirality hasn't done anything. But how did these appear? When over here, the bouncing back and forth waves have the same wavelength, and it's easy to understand where these nodal lines come from. But here, the wavelengths going this way and that way are different, and yet the nodal lines appear in the same place. Well, to understand what's going on, Benjamin did these simulations where we could look now at the amplitude as it evolves in real time. So without the chirality, this lowest mode, which has the nearly single node in the middle, is an amplitude which everywhere is symmetric about the center of the element. So it's just increasing up and down everywhere at the same rate. So this side and this side are the same. The middle is going up and down. It has a certain symmetry about it. The same mode with the chirality, we can see what the chirality does. So here, right and left traveling waves have the same wavelength. The one I'll show you now, the wavelengths are different depending on whether you're going right or left. In this case, it's much more interesting and pleasing to look at. And you see it looks like a wave just traveling along and wrapping itself around and traveling back through. But it's still, the amplitude over here is bounded, just like this was bounded. The amplitude here is a node, just like this was almost a node. But you get this nice, beautiful flowing. That flowing is a phase velocity. That phase velocity is directly proportional to the strength of this chiral interaction. So we see a beating of these waves. Now, seems almost trivial. That's exactly what you would expect. You have an envelope. The nodal structure is defined, and it's the same with or without the chirality. But the partial waves are trapped beneath this envelope, and they are traveling with a well-defined direction determined by this chiral symmetry breaking interaction. Now, one of the nice things about this is, in practical terms, if you're doing an experiment like ferromagnetic resonance, which I've seen you do here, the ferromagnetic resonance is a particular experiment where you're using microwave electromagnetic fields which are uniform across whatever the sample is that you're studying, and they only couple to an oscillating magnetization that is everywhere together in phase. So you only see modes that have a net magnetization, in other words. That's why the spectra here look different. Here, the ferromagnetic resonance only couples to the oscillating magnetization, which are exactly together in step, in phase. Here you get many more new peaks because this is a plot of the intensity. It's not a plot of the amplitudes, the time-dependent amplitudes. So ferromagnetic resonance can couple to all of the modes in the system with chirality. They can't see without chirality. And it's because of this difference. When this has its maximum amplitude, it's not in phase with that. So the electromagnetic wave couples to the net magnetization. So it's a practical idea for a new type of experiment which should be able to measure the strength of the chiral interaction, which is a very difficult problem experimenting, using very simple standard ferromagnetic resonance technique. Okay, so I'll talk very briefly now about some other ideas of how to create artificial magnets which have properties we can design. The idea is based on what's grown out of spin ice research. And spin ice, just for those, if you're not familiar with it, it's called spin ice because it's based on the idea that in ice, water ice, this was pointed out many years ago, that these are hydrogen bonds, and there's a dipole moment associated with the position of the hydrogen in the bonds, and it cannot have the same order, the same ground state ordering everywhere throughout the crystal, and there has to be some frustration. And the reason is because the geometry does not allow you to have the arrangement of these bonds such that they have the minimum energy in exactly the same way throughout the entire crystal. The geometry of the crystal does not allow it. So these are geometrically frustrated crystals. Spin ice is the direct analog. In spin ice, it's not dielectric dipoles, but it's magnetic dipoles which are frustrated by geometry. And artificial spin ice is what these are, where one tries to capture this geometrical frustration of the ordering of magnetic moments. And so here's a close-up of one type of artificial spin ice. These are magnetic elements. They're only a few hundred nanometers long, and they are designed to be single domain magnetic elements, so they either point along the element or up or down or right or left. So they're constrained. And then the geometry is determined by this fabrication. They interact because they are magnetic moments. They generate magnetic fields. They have north and south poles, and they want to align north and south. So this geometry is not really frustrated. It has an anti-ferromagnetic ground state. This geometry, which is very similar, has a ferromagnetic ground state. But what you can do with these materials, by using lithography, you can make anti-ferromagnets and ferromagnets. These are artificial ones. But you can do much more. You can do things which cannot be done in nature. This, for example, looks a little bit like this square lattice. But if you look carefully, you've taken each side, you've split it, and put in an element in between. And if you count the sides along an element, there's 1, 2, 3, 4, 5. This is how you take a pentagon and fill space in 2 dimensions. So you can only do that on a football, right? Pentagons fit full space on that. You can't do it in 2 dimensions. We know that in solid state physics. It's the first thing we learn. Here, magnetically, it is. You can't do that so easily in nature, but you can do it here. And what was discovered here, this is called the Schottky lattice. And when this was fabricated and measured, it was found to be truly frustrated with the type of emergence frustration, which means that there are many degenerate ground states that can all be identified with the different orderings of these elements. So that's just one example. You can start to manipulate in fundamental ways even the entropy, the way a system can have entropy in its magnetic ordering. So anyway, so what I'll talk about though is just a concept. It's an idea for magnomics. So here's this array I started out with, the antiferromagnet. These are the little moments with north and south poles, and they interact by dipolar fields, so that it's an antiferromagnet because you want to have north next to south as much as you can, and that's the strongest interaction. So you have 2 spins out and 2 spins in, which defines an antiferromagnet. It's also called the spin ice rule. And that's all governed by the shape and the spacing of the islands. When we looked at this, as part of, this was Zoe's PhD work, she showed that, at least theoretically, we could control these configurations to a large extent. So we could maybe pick domains, antiferromagnetic domains, and separate them with domain walls, and then manipulate them, move the domain walls, change the shape of the domains. So you could control it. There's schemes for doing that. Why would you want to? Well, point of view of magnonics, by exactly the same way that we have the domain walls that trap spin waves, maybe we could do the same sort of thing with these crystals, these artificial magnets. So we've made some samples. These are square spin ice, and they've been studied using inelastic light scattering in Brillouin scattering technique, which is useful for measuring spin excitations at low frequencies. Just light is in and it's reflected, and one looks at the off-specular reflection of the photons, because these lose energy and momentum to spin waves inside the system. So that can be detected using an interferometer. And this is example spectra. And the first thing we did was one can change the angle of incidence and thereby control the coupling of the momentum of the light to the spin waves. And we looked for evidence of a band structure forming. And that's what these are. This is frequency versus the in-plane momentum. And they're completely flat. So we saw no dispersion at all within the experiment. So these are not that kind of a magnonic crystal at all. But instead, what we did see were very rich spectra, and we could identify the spectra as being these normal modes of the elements that I showed you earlier in the case of chiral interactions. And so we could use simulations to try and identify the experimental modes and their character. And we see then that there's two different frequency branches, and these correspond to modes which are large amplitudes in the center, and also then higher frequency modes where you have local modes just trapped to the edges. And when we put the field along a symmetric direction like that, we see that we can understand all of this as just being both elements that are at this orientation with respect to the field and elements at that orientation with respect to the field. If we change the direction of the magnetic field, we get a much more complicated spectra. So the field is now along one of these, where we're aligning the magnetization parallel in these elements, and then it has to go in a perpendicular direction in these elements. And here, then we see, again, a very rich spectrum of modes, which we can understand more or less in terms of the micromagnetics. And so, even though this structure is not a magnonic diffraction grating for spin waves, it contains within it resonances that can be controlled by orienting the magnetic moments. And as I said, we believe we can do that and control our orientation of the elements. So we should be able to control this spectra of resonances just by changing the ground state of the magnetization. And so we've done simulations on this. So for example, if we've got an antiferromagnetic arrangement separated by a domain wall, there are resonances associated with the domain wall that we should be able then to manipulate. So there's now quite a number of people in the United States and Europe who are trying to do this sort of manipulation of the spin waves and the resonances using these various kinds of geometries. So that may be something where we can create another way of manipulating microwaves and reconfiguring the microwave devices without having to build a new device. The last thing, if I've got, do I have some time now? A little bit. Or is it yours? Okay. just mention something else. Everything I've talked about for spin waves so far has been in microwave region, so it's in the low gigahertz. But antiferromagnets, which would have two sublattices, each sublattice being ferromagnetic, have different sets of energies, and they have different responses. And typically, these are at much higher frequencies. So rather than being in the gigahertz, they typically have frequency response in the 100 gigahertz or even the low terahertz regime, if not higher. Now, in that case, one needs to think about spin wave excitations there as not being uncoupled, that they can be coupled strongly to photons. So magnetic excitations plus photon excitations, and this object is a polariton. I mean, they're fairly common. Any of us who are wearing these are seeing objects because it's a polariton inside the spectacles, and then the photon in free space interacts with the polariton, transmits through, and we use the various phases to focus the light, diffract it, and all of that. So the key thing for the antiferromagnet then is the permeability, because that's the magnetic response that determines the dispersion inside the material. So this is determined by the magnon spectrum, and the key point is we can control it with a magnetic field. So in no magnetic field, there's a single resonance in a simple antiferromagnet. With an applied magnetic field, that resonance splits into two different modes. And that is simply because we have a unit cell here, which has two different members with opposite orientations, and we split their energy with a magnetic field. So it's a diatomic crystal in that sense. So these two resonances exist, and it's near these two resonances that the material is highly dispersive, and that's when the index of refraction changes most quickly. So if we're looking at excitations near these resonances, things become very interesting. And what's most interesting is, you see, I've written this not as a number, but as a tensor. And that's because there are off-diagonal elements associated with these resonances. And the off-diagonal elements near the resonances may even have different signs. One may be positive, and one may be negative. We achieve that in metamaterials, and we understand that as a negative refraction, for example. And so this was work that's been done in collaboration with Tom Dummelo, who's in northeast Brazil, and our student, Jair, who has been doing these calculations. And so the idea is we're looking at antiferromagnet, can have multiple resonances. We're interested in what happens near those resonances. So if we plot frequencies like that, then this is just to sketch out how you would couple these resonances with light. This is the light line. And near the resonance, you deform then the polariton dispersion. So it's both magnetic and electromagnetic. And this is the part here where, because of the off-diagonal elements of the permeability, you can have interesting and new kinds of optics. This is a map, a schematic map of the dispersion relation just of the magnetic excitations. Everything is governed by where these resonances lie. So in an antiferromagnet, and these are the light lines on the scale of the magnetic excitations, these are the regions where the resonances are positive. The regions where the resonances are negative are in here, and you can now also have additional excitations which are localized to the surfaces. But I'm not going to talk about these. I'm just going to talk about what happens to these regions where we've got a strong coupling to the electromagnetic spectrum. So here's two examples. The first one being, we have a Gauss-Hanschen shift, where if we look at reflection of light from an antiferromagnet, then there'll be a shift. So you come in with light, and rather than having it bounce off exactly here, it appears to bounce off inside the material down here. So it's shifted. And the direction of the shift depends on the direction of the magnetic field. Now what's going on is that we consider this to be not just a ray of light, but it's a beam of light. And if it's a beam of light, then there's a distribution of wave vectors parallel to the surface, and it's an interference effect. All the things about non-reciprocity I talked about before come into play here, because applying a magnetic field changes the way in which the waves can add up constructively to form a reflected beam. And what's maybe unique about magnetic system is you can tune the degree of the shift with a magnetic field, but it also occurs at normal incidence as well as at oblique incidence. Now, what happens to the wave which is transmitted? That was the next bit. Well, it turns out if you're working near the right frequencies where the different elements of the permeability tensor change sign, then it can, the beam comes in as incident, there's some reflected, and the refracted wave can go the wrong direction. It can go backwards and then come out. So it behaves like a negative refraction material. But there's no metamaterial here, it's just a single film. And you're exciting it at the right frequency so you get the correct interplay between the elements of the geotropic permeability. And what this means then is we also have the possibility of slab focusing. So here's an antiferromagnet film, the source, single point source, and here's negative refraction through there, brought through a focal point inside the material and then out again. And I've shown it here, if there's additional feature here, is if there's no damping, if the damping is very low, then you can start to see fine structure in the light, which is because of the shape of the response of the dispersion. It's a hyperbolic material, I'm saying. And so it adds up in a way and forms these crossing rays which interfere with one another in such a way as to form this regular lattice of points. So an interesting thing to explore here, I think, is are there phase discontinuities at each of these junctions as you would have in light. But in any case, that's just two examples of the optics in a magnetic material such as an antiferromagnet that is waiting there to be explored. No one's done experiments on this. So anyway, and so that's all I had to say, talking about spin waves and what can happen when we lower the symmetry in such a way, which is possible now in magnetic crystals and magnetic films even, and what happens when they interact with some of the structures inside the magnetic films, and then some of the interesting puzzles that can occur when you think about this non-reciprocity and the chiral lack of symmetry when chiral interaction. And then concepts for microwave devices based on reconfigurable elements, and others where the configuration of the element is just the permeability, but it has properties which at certain frequencies have direct analog to what we see in metamaterials. With that, I think I've finished, and I want to thank you.
Thank you very much for a nice talk. So, I think it's time for questions, comments.
I was wondering, for the case that you're describing for the artificial magnetic materials, you described that frustrated structure. Is that so that is a real experiment? I mean, it's a real.
Yeah, this one I showed you very briefly.
Yeah. So I was wondering, you mentioned about this 5-point symmetry. Does these kind of systems have properties like quasi crystals? Like when you have this. It seems to be something new. Does everybody try that? I mean,
well,
perhaps for transport properties or so?
Well, the lab that made these systems also made, it was a Penrose tiling,
Okay.
like that. And yes, it's been tried, there are results, and I don't really understand them.
I see.
So,
All right.
there's things going on, but no clear picture
What's going on?
of
Right.
what's going on exactly. So, I mean, that's one example. There's been, most recently, just a few weeks ago, it was published in Science. Someone took this lattice and mixed it, I think, with something like this. And it's basically it's periodic, but it is still a new kind of structure, a super lattice. And this one, it enabled them very easily to configure it with a magnetic field. So yes, you can build anything, really. Some people even looking into 3 dimensions. So it's an area that I think is growing, and I think it's precisely because it moved away from thinking about just frustration and moved into thinking about how you can engineer new kinds of material physics and properties.
Thank you.
Any more questions? So I have a question. You shown here several fascinating phenomena related to magnonics. How do you think? Because it's very interesting from the fundamental point of view, of course, of physics. But we are invited to think about new applications of this. And you think that this is a new. Is your opinion about the applications in the next future, or it's too far yet?
Well, I think one of the attractions, people have been looking at different kinds of pattern materials in magnonics for many years, with the idea of having an alternative platform for computation. Now, why would you do that? Let me go back to this slide at the very beginning of this point. Yeah. Okay, so people have done that from 2 different points of view at least. One is just the elements reversing. You can build up geometries which function as logic gates. Now, and you can do this with wires, and domain walls, and networks. And why would you do that? Well, one reason you can do it is because, in principle, this can be achieved very close to thermodynamic limit on manipulating information. It's called the Landau limit. So the idea is that if you think about the work done to change the state of your information, it can be done, and it's been demonstrated experimentally that you can approach this limit with this reversal magnetization in single particles. So, if you wish low power computational electronics, that's a good place to look, or some analog to that, might be magnetic. So that's one area. Spin wave excitation is again another alternative for low power spintronics. And it's low power in that, when I say spintronics rather than magnonics, because in some sense these 2 fields are overlapping strongly. In spintronics, we now know that it's possible to have pure spin currents and convert them to electrical voltages that fit within sort of electronics we use daily. But spin currents can be manipulated with much less loss to Joule heating. And a spin wave is carrying exactly that information. So it's transporting angular momentum information about angular momentum from one position to the other without a motion of electric charge. So you do not have Joule heating. So again, that is a low power alternative to conventional electronics. The idea is this thing gets hot. Most of that energy is wasted. Okay, maybe a lot of it is the display, but it's certainly happening with the processors as well. So these magnetic-based devices, magnonics and spintronics, coming closely together, but they offer possibility platforms which are very energy efficient. And this is the whole motivation for skyrmion research, because the skyrmions, when they were first observed in magnetic materials, was very quickly followed by people putting on currents through them and discovered that one can move the skyrmion with very, very small electric currents, orders of magnitude smaller than is possible in some of the other systems. And pure spin currents will interact, spin waves will move slowly. So, and the skyrmion is you can localize information there within a structure which is maybe 100 nanometers or less in diameter. So it's quite small. A stable structure, long lived. So I think for achieving a replacement, or the next successor, I should say, for conventional electronics, then this is a real candidate.
More patience. Any more questions, comments? So if not, let's thanks speaker again.